Hey everybody, this is Mr. Bortnick for AP Calculus AB. This is Unit 1, Limits and Continuity. Today's topic is topic 1.15, Connecting Limits at Infinity and Horizontal Asymptotes. Enjoy today's notes. All right, for section 1.15, Limits at Infinity and Horizontal Asymptotes, we're going to remind us first what horizontal asymptotes are. And so if we think about what a graph is, if we've got a given function, we're very familiar with like vertical asymptotes, right? We have this idea that, if we have a vertical asymptote, right, like this, we know that the graph from the last video would need to either go up along that vertical asymptote or potentially down along the asymptote as well. And we know that, at that particular x value where the vertical asymptote is, that the function is not defined, right? There's no actual point there. The graph would get really, 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 really close to that vertical asymptote, but never actually touch it. Now, this is different from, if we back up, what we refer to as a horizontal asymptote. Now, a horizontal asymptote, unlike a vertical asymptote, is essentially what we think about a graph approaching as it goes really, really far to the left or far to the right. And so sometimes what we might see is a function getting, as the graph goes on, gets really, really, really close to that line and never really crosses it. And we say that as it approaches infinity, that graph is going to get really, really close to the asymptote. Now, one thing that's different from a horizontal asymptote versus a vertical asymptote is you could actually have a function cross a horizontal asymptote. It could cross it as many times as it wants. Sometimes we have functions like this that we refer to as it oscillates. So it bounces back and forth along the asymptote, getting closer and closer and closer to it as time goes on. And as we go further and further towards infinity, it's going to approach that asymptote. So again, unlike a vertical asymptote, horizontal asymptotes, you can cross the actual function, or the actual asymptote. But why is it useful? Well, it tells us what happens to our graph as it gets closer and closer and closer to, like, x is approaching infinity, or even in the opposite direction, as it goes towards the left, as x is approaching negative infinity. And so using this idea of horizontal asymptotes today, we're going to be talking about limits at infinity and how those relate to these horizontal asymptotes. We're going to be looking at problems like this, where we're talking about the limit as x approaches either infinity or the limit as x approaches negative infinity. And these ideas of horizontal asymptotes and these limits towards infinity are the same idea, just, there's very similar ideas, if not the same idea for that. And so our question here is, what does the y value approach as the x value approaches negative infinity and positive infinity? Does it approach a specific number, or is it growing without bound? So, for example, a graph that might be growing without bound would be something like, the e to the x function, right? We might have something like this where it just goes up and continues to go up forever. We would say that this is growing without bound, as opposed to this situation over here where it's growing towards a specific horizontal asymptote that we've got here. And so a function could either grow without bound, that would be saying, it's going towards infinity, or it could be going decaying without bound, be going towards negative infinity in that case as well. All right, so some basic rules for horizontal asymptotes from our notes that we've got here. In these cases, when we're trying to figure out what a horizontal asymptote is, we are comparing the numerator and the denominator of a fraction. And so in this case, if the denominator grows faster, that means we've got, not as big number in the numerator, but we've got a really big number in the denominator. If I'm dividing by a really, really big number, that fraction is going to get closer and closer to 0, right? And we can think about that, for example, if we were to say like 1 over a million. 1 over a million. If we were to do that, the bigger that denominator is, the closer this fraction is going to get to 0. And so if your denominator grows faster, that means that the limit is going to approach 0, or the horizontal asymptote would be 0 for that function. If the numerator and denominator grow equally as fast, if they grow the same speed, then we have essentially a big number divided by a big number. In those cases, it's going to be equal to 1. Or as what we're going to see is it's going to be the ratio of the coefficients of if they've got the same exponent in this case. And then finally, if the numerator grows faster than the denominator, then you have a big number being divided by not as big of a number. And so in that case, we would say that it's going to head towards infinity, right? If I were to have a really big number divided by a very small number like that, or 1, or even a decimal like that, that fraction is going to get larger and larger and larger and larger as that numerator gets larger and larger and larger and larger as well. And so sometimes we're thinking about, how fast are these functions in a numerator and denominator growing so that we can determine what the horizontal asymptote is going to be. In that case, we need to think about and we need to recognize which functions grow faster as x values grow larger and larger. So we need to recognize which functions grow faster as x values get larger and larger. So we have some functions here. F of x is equal to x squared, x cubed, x to the 10th, 2 to the x, e to the x, 4 to the x, and the natural log of x. Let's see what happens as x values increase. So I've made a nice table for us. We notice looking here when x equals 1, the largest one on this list looks like 4 to the 1, looks like this right here. That's our largest value. And when we look at x equals 10, ooh, these numbers are getting big. We've got 100, 1,000, 10 to the 10th power, even 1.05 times 10 to the 6th. Our largest one here appears to be 10 to the 10th. That's a pretty big number, 10 with 10 zeros after it. What about when x equals 100? Well, in this case, we've got a lot of scientific notation here, but looks like 1.6 times 10 to the 60th is a absolutely huge number. That's going to be 1.6 with 60 zeros after it. That's a unbelievably large number. And similarly, when x equals 1,000, super duper big is what we would say for that. Even bigger than this 10 to the 301 power for it. So if we're going to rank these from fastest growing to slowest growing, what's the fastest growing one? Well, we see that this 4 to the x is very fast. In fact, that is the fastest one that we've got here. And even closer, e to the x, e is like 2.71, slightly larger than 2. This would be the third one. And then we see that decreasing of these powers here, it is growing a little bit as quickly. And this natural log of x is actually the slowest of the bunch. So that is the slowest one. Now, how do we figure out how quickly something is going to grow? In general, a rule that we sometimes refer to as FEPL. FEPL. And that's just sort of a shorthand way that I remember the order that things grow. What this stands for is factorials, which actually doesn't come up much in AB calculus at all. And then we've got exponential functions. So something like y equals 3 to the x would be an exponential function. Then we've got polynomial functions. So like y equals x to the 10th plus 3x squared, blah, 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 blah. And then we've got logarithms. So that would be, for example, y equals the natural log of x would be an example of that. And sorry, I should give an example of a factorial. So we might have something like y equals x factorial with this little exclamation point. Again, this one over here on the left side, factorials don't show up in the AB calculus curriculum, but it is useful, thinking if you're planning on taking calculus in the future. So what does this tell us? Well, it tells me that actually, if we give it enough time, exponential functions will always grow faster than polynomial functions. And if we give it enough time, polynomial functions will always grow faster than logarithmic functions. And so if we're thinking about these problems that are approaching infinity, right, the limit as x approaches infinity, right, that's as much time as it needs. And so if it's going towards infinity, we really would expect always exponential functions to grow faster than polynomial functions always faster than logarithms. Okay, So within those categories, though, we can obviously compare them. Notice here, up here, we had 3 different exponential functions, 2 to the x, e to the x, and 4 to the x. As the base got larger, notice it was faster. It was growing faster than those other ones, right? These numbers were growing much more quickly for 4 to the x than it was for 2 to the x. Within our polynomial functions of x squared, x cubed, and x to the 10th, we notice that as the exponent is larger, it grows faster than those other functions that have lower exponents. And so oftentimes in AB calculus, we're almost always comparing polynomial functions. This is the most common one that we're looking at, is this grouping of polynomial functions. We know that the larger the exponent is, the faster it's going to grow. And so that's a key piece. The larger the exponent, the faster a polynomial function grows. Now, let's reframe us before we get into practice here. Why do we care how fast these functions are growing? Well, if we go back to what we were talking about before, if we have a fraction, right, that has a small number and a large number, we should be able to tell, looking at which one's growing faster, to tell whether the limit is going towards 0, or whether it's going towards 1, or whether it's growing without bound towards infinity for that. All right, let's take a look at some practice problems. So, find the horizontal asymptotes of each function. So this is equivalent to us finding the limit as x approaches infinity. In this case, we're looking at this first function, y is equal to x squared plus 4 divided by 3x minus 5. Here, the only parts that we actually care about for these functions are the terms with the largest exponents. I only care about the x squared and the 3x. Because if this is growing without bound, if it's going towards infinity, infinity squared is so much bigger than 4, right? Infinity squared is going to be so much bigger than 4 that this 4 doesn't really matter. And 3 times infinity is so much bigger than -5 that this -5 really doesn't matter. So I'm going to not even really consider those two parts of this. So I'm looking here at x squared, and I'm looking at 3x, and I notice that that x squared has a higher exponent than my 3x. So because of that, that numerator, I'm going to have a really big number divided by a smaller number, and so that tells me that this is going to be going towards infinity. So that this would be growing without bound for this. And so because of that, we would say that this has no horizontal asymptote. No horizontal asymptote. All right, well, let's try this next one. For y is equal to x plus 4 divided by 3x minus 5, similar idea. I only care about the largest exponent terms, that x and that 3x. This is very similar to the last one in that, you know, infinity is so much bigger than 4, and 3 times infinity is so much bigger than -5 that I don't really care about those parts. But here, we notice that the exponents on these are the same, right? It's x to the 1 and x to the 1. And so in cases where the exponents are the same for those largest terms, we would, they're essentially going to cancel out, right? This is going to essentially be like x divided by 3x, and those, like, we're going to be left with the coefficients. This is like a 1x divided by 3x, so that's going to be 1/3. So this particular equation, if we were to graph it, would have a horizontal asymptote, I'm going to just put HA, at y is equal to 1/3. And if you graph that function, you would see that as it gets closer and closer towards infinity, that it would go towards 1/3. What about 6? Well, our largest term in the numerator is x. Largest term in the denominator is 3x squared. We're going to have some values, again, the 4 and the -5 don't matter here. But here we see that the denominator has a larger exponent. And so what I'm going to have is a small number in the numerator divided by a very big number in the denominator. That's going to tell me that this is going to go towards 0. So I would expect this function to have a horizontal asymptote at y equals 0. Which if you graphed it, you would see that it gets closer and closer to 0 as you go further and further towards the right on that graph. What about this one? Well, In this case, it's sort of tough. It's really nice that this is factored because maybe we could see, whether it's got removable discontinuities or asymptotes. But for the case of finding horizontal asymptotes or these limits towards infinity, it's not particularly helpful to have it factored, right? We need to compare the largest termed exponents. And in order to do that, we need to sort of re-expand this out. In fact, for that numerator, if we do that, we're going to get that this is x squared plus 3x minus 10. And in that denominator, if we do 4x minus 3 times 4x minus 3, that's going to give us a 16x squared minus 24x plus 9. And again, now that this is expanded, I'm only worried about the largest exponent terms, right? Because those terms are going to grow the fastest. I am not worried about the rest of this, right? I'm not worried about my 3x at minus 10 or my negative 24x plus 9. And we see in this case, if we compare the numerator and denominator, that this is going to be going towards 1x squared over 16x squared. Those have the same exponent, and so because of that, I would expect this to go to those coefficients, 1 over 16. So y equals 1 over 16, there would be a horizontal asymptote at that particular value for number 7. Now, remember earlier when we said that the limits can go towards either infinity or negative infinity? They can go to either one of those. In this case, if we're thinking about the two that we've got, all of these problems that we've gone so far, I haven't talked about whether they're going towards infinity or negative infinity because they have one horizontal asymptote. Sometimes functions go to a horizontal asymptote in both directions, the same value, and sometimes they don't. Sometimes, for example, these actually could have two different horizontal asymptotes. Right? If we actually think about what this might look like, I might have a function like this. We have a function like this where it's got a horizontal asymptote up here and a horizontal asymptote down here. And maybe I have a function that starts off at the origin, goes towards this horizontal asymptote and goes like this, but in the negative direction goes towards a different horizontal asymptote. That is totally all right. This just has two different ones. One when x is approaching infinity, and one when x is approaching negative infinity. In this case, 8 and 9 are some examples here where they're not going to be going to the same ones. How do we know that? Well, we can think about what's happening in the numerator here. We can see that whatever value we plug in is being squared and then taking the square root of it. And so it's going to give us some different behavior from if we plug in different values. So what happens? Let's think about what happens if we think about what happens with infinity. Well, again, I'm not really worried about any of this. This is like smaller stuff, so is that -1. So if I do the square root of 4 times infinity squared divided by 3 times infinity, right? Infinity squared is a large number. It's a positive number. If we multiply by 4 and we take the square root, we're going to end up with 2 infinities, right? Because the square root of 4 is 2, and the square root of infinity squared is infinity. And then that's being divided by 3 infinities, and we can see those cancel out, and that's going to go towards 2 over 3. So one asymptote, horizontal asymptote, is at y equals 2 over 3. What happens, though, if this is approaching negative infinity? Well, if we plug in a negative number, we can see that that negative infinity is going to get squared, and that's going to multiply by 4, and then we're going to take the square root. Now, squaring it is going to make it positive, and then taking the square root is going to keep it positive. So that numerator is going to still be 2 times infinity, but the negative's gone away. And in the denominator, we've got 3 times negative infinity, which is -3 infinities. Our infinities would cancel, and so this would be approaching y equals -2/3. So this is an example of a problem that has 2 different asymptotes, one at 2/3 and one at -2/3. Now, does that happen every time when there's a square root? No. So we can see the same idea for this next problem. Let's imagine, again, x approaching infinity here. I'm not worried about the smaller terms here. I'm only worried about the largest exponent terms for these. And so if we do this, this is the square root of 4 times infinity to the 4th divided by 3 times infinity squared. Well, that's going to be 2 times infinity squared divided by 3 times infinity squared. Those infinity squareds would cancel because they're the same sort of exponent. So that tells me that this is going to 2/3. If we do this with a negative infinity, we're going to have the square root of 4 times negative infinity to the 4th divided by 3 times negative infinity squared. Because this is a positive exponent, or rather an even exponent, negative infinity to the 4th is a positive number. That's going to give me the square root of 4 times infinity to the 4th, which again is 2 times positive infinity. Right? Raising that to the 4th power essentially made that positive. But that also happens in the denominator. By squaring this negative infinity, that's going to make it a positive infinity as well. And so that would be 3 times, so 3 times infinity squared, and those infinity squareds would cancel, giving me 2/3. So we see in this case that both the y values, the y is equal to 2/3 when x is approaching infinity, and when x is approaching negative infinity. So both of those would be the same. All right, number 10 and 11, let's go into this. In order to do these, I just want to give really brief background knowledge and remind you what the e to the x function looks like. So what does this function look like? Y is equal to e to the x. Some key things you should know about e to the x is it is a exponential growth curve that looks like this. It goes forever. And it has a horizontal asymptote at a height of 0. And it goes through the point 0, 1. Pretty much if you know that about exponential functions, you know mostly what you need to know about the e to the x function. But it goes to the left along this curve in the negative direction, gets closer and closer and closer to that asymptote, but never touches it. It crosses 0, 1, and then it grows forever with that exponential curve. All right, so let's jump into number 10 with that knowledge. We've got the limit as x approaches infinity of negative 4e to the 1 over x. In this case, you know, we can think about what would happen if we plugged that infinity in. This would be like negative 4e to the 1 over infinity, which 1 over infinity, a small number divided by a very, very, very large number, is going to approach 0. So this is like negative 4e to the 0th power. Well, thinking about our graph here, e to the 0th power is 1. So this is negative 4 times 1, or negative 4. So that is going to be our number 10. For number 11, we have the limit as x approaches infinity of 5e to the negative x. Same idea. Let's think about what would happen if we plugged in that infinity. Now, for 10 and 11, we can't actually plug in infinity, right? Infinity is not a real number. We're not actually evaluating these. We're just thinking about what the function is doing when we plug in as large of a number as we can think of. And so if we do this, we have 5e to the negative infinity. And thinking about our rules about negative exponents, this is the same thing as 5 times 1 over e to the infinity. E to the infinity is going to be a very large number. We said that this grows without bound. It goes forever. So 1 over a very large number is going to go towards 0. So this is 5 times something that's going towards 0. And so our overall answer for this limit would be 0 for number 11. All right, number 12 through 15. How do we do this with trig functions and horizontal asymptotes? Well, starting with number 12, we see that we've got the limit as x approaches negative infinity of sine of x over x. Ooh, this looks like one of our special trig rules from earlier in this chapter. I remember when we had sine of x over x, and we said that that limit was always equal to 1 when we did that. However, key piece when we did that earlier in this chapter is we said that this rule only works when it's the limit as x approaches 0 for this. So this was one of our trig rules from earlier in the year, or special trig rules. But that is not actually applicable for number 12. Even though this is the same part that's inside of our limit, this rule only works when the limit is approaching 0, and here we're talking about negative infinity. So that is not going to help us out for number 12, unfortunately. So how do we approach this problem? It's going to be useful for us to think about, what does the sine of x function look like? What is sine of x? And we know from geometry and maybe from Honors Algebra 2 that the sine of x function, if you were to graph it, is this function that's got this thing that's called a sine curve that goes up and down forever in both directions. And one of the key pieces about a sine wave, or the graph of sine of x, is it goes up to a value of y equals 1, and it goes down to a value of y equals negative 1. Now, if I were to continue this graph forever and ever, it's going to continue that pattern forever and ever. We refer to it as an oscillating function. It oscillates back and forth forever and ever. And as it goes towards infinity or negative infinity, it's going to continue oscillating. So I know that this numerator is going to be oscillating for sine of x back and forth between 1 and negative 1 forever. And it's being divided by x, which is going to end up being a bigger number, or in this case a very, very small number because it's going towards negative infinity. So I have a number that is stuck between negative 1 and 1 being divided by a larger number. To me, this limit has to be going towards 0 because the denominator is getting bigger and bigger. If we think about our rules, when the denominator gets bigger than the numerator, over time, that limit is going to go towards 0. What happens for this one? Well, I'm going to think about what happens if I plug in my x here. I got negative 3 cosine of 1 over a very large number. We have a very small number being divided by a very large number. In that case, this part is going to be going towards 0. So I would expect this to be like negative 3 cosine of 0. And cosine of 0, if we think about what that's going to be equal to, actually equals 1. So this is negative 3 times 1, or negative 3 for problem number 13. Number 14, hey, this is just a sine of x. And we had talked about over here the graph of sine of x just oscillates back and forth forever and ever. If it's going towards infinity, it's going to still oscillate back and forth. And it's not going to any particular y value. So because of that, we're going to say because this thing is oscillating, that this does not have a limit. The limit does not exist. It does not actually equal any value. It's never going to stop anywhere between negative 1 and 1. It's going to just keep going forever and ever. Okay, what about this infinity for both of these? Well, we would have essentially 5 times infinity times cosine of infinity. And we know that the cosine is going to be similar in a sine wave like sine is. But the infinity is going to be making this get larger and larger as it goes. And so what would I expect this graph to look like? I'd expect it to sort of look like start off as a sine wave, but it would be getting larger and larger because it's getting multiplied by that x value that's going to make it bigger and bigger. And so it's going to just oscillate back and forth. This also would not exist. Oscillating and does not exist would be my answer for number 15. We've seen these limits towards infinity, negative infinity, a couple of different ways in our practice problems. Please try these out and see how they go on the practice that we've got. Check your answers on the posted answer problems, and then check out the test prep problems as well. See if you're feeling confident with it. If you have any questions, please feel free to stop by class or office hours and ask them. Have a great rest of your day.